Welcome to the second session for the hands-on simulate series. That is going to be specifically on battery simulation. My name is Yasser Shakil Siddiqui. I'll be the host for today. For today's session, we have an expert for battery simulation from Siemens, Kaushik Ilya, who will be giving the introduction of this session. So just a quick overview. Welcome to the Hands-on Simulate series, and it's aimed essentially at providing users a hands-on experience with SimCenter Star CCM Plus. As mentioned before, the series we will be solving some of the toughest industry problems using the tool's advanced capabilities. Today's session is going to be on battery simulation. We've had a previous session where we covered the introduction of the product, did a product overview as well as a workflow demo. For those who still have certain licensing issues and cannot connect to the tool or do not have the recording, please don't hesitate to email me after the session and we'll provide all the relevant information and help. So let's just jump into the agenda for today. So we're going to start with running through a battery design in Siemens portfolio that will be covered by Kaushik. Followed by that, we're going to have a hands-on workshop where we will be working on designing a battery pack, which is built ground up from a cell design with its electrochemical properties, configurations, and connection setups, which is all done using a inbuilt custom workflow within Star CCM Plus. A design optimization study based on the select design variants will also be conducted. And finally, we'll showcase how we can integrate 1D and 3D solutions, and in this case, in the concept of battery design. Know that today, what we will be covering is specific to battery simulation, but a lot of the concepts and features can be used across different domains and industries. So without further ado, I'd like to pass on the baton to Kaushik to present today's introduction of battery design within the Siemens portfolio. Kaushik, it's all yours. Hi, Kaushik. You might be possibly on mute. Could you just unmute yourself?
Oh,
We can't
sorry.
hear you.
Can you hear?
Perfect.
Can you hear me now?
Now we can hear you. Wonderful. Thank you very much.
Okay. Okay. Perfect. All right. So, let me just close that. Okay. So the key takeaways that we would like you to focus on from this presentation is how the SimCenter portfolio can be deployed and throughout the V cycle for varying aspects of the battery pack design, which can be cycling, aging, a normal operation, or a thermal runaway. And the same strategies can be applied to each of those analysis. Um, I'll cover what are the different steps in the development cycle and what would be the right tool to address that, and I'll showcase probably with a case study later on. Okay. Okay. So for a battery development cycle, right, first I want to capture what is needed at the system level. And based on the system level, like in terms of range, anxiety can be an issue, and the performance or how much heat that it generates, all of those performance requirements, once I've captured, I then can design a cell or a pack based on that initial specifications that I have. Once I have my cell design, then I can do a more detailed analysis to deal with packs complexity, which not only includes electrochemical, but thermal as well as electromagnetism, as there are bus bars and you need to account for the ohmic heat. So that detailed model is necessary to look at different attributes. And then you could use that detailed model to create a system level performance for varying performance criteria that you have, not only at the battery pack, but if there's hydraulics involved, if there are electrical machines which are involved, and how it all ties in together, that can be done with a system level design. And then at a prototype validation and certification, You can do a hardware in a loop kind of a test. And then you could also feed that information back into your initial design once if there's an IoT based device to improve on the very design. So we need to characterize the cell model, then validate on the pack model, and then test it, which can be cumbersome. And that's why there's a need to do like a simulation point of view to capture the 3D aspect as well as the 1D aspect. So there are pros and cons on each of them, right? So I get a realistic model through testing, but it's expensive. With a 1D model, I can do complex systems, but may require inputs from varying levels of components, which can be combined with doing a detailed model to get those input parameters, but these are computationally efficient. But the SimCenter solution can address that three aspects in a very coherent way. Yeah. So this is to extend from what we spoke about. So creating that digital twin of the product from not only at the electrode level, but at the cell level and pack level, and how it needs to be produced, what nothing spoils, and what is the process for that entire cell to pack level creation can be simulated with the digital twin production solution. And then once I have my product out in the field, I can feed that information back through IoT devices to improve on my product, which creates a holistic digital twin. So what are the different challenges that one faces with battery packs? I want to account for what would be the effect of tortuosity or what is the potential drop across the half cell electrode, and what would be the effect of binders being added or conductive agents being added. So at the cell level, this is what cell designers would want to look at. At a pack level design, one would want to understand the effects of my drive cycle on the thermal load, as well as if it's a stack-based cell, there would be expansion and contraction or cell breathing, which creates stress. And how can I mechanically control that stress by including braces, and what should be the pressure that I need to account for? And these packs itself don't sit in open air, or they can. So you could have different kind of fluid domains. It could be water or oil or air-based, and you can see whether you need more effective cooling to keep it in an operating range. So for the initial design, we would start off from the system level spec. And once I have a system level spec, I could choose a battery design and validate battery requirements with other vehicle level requirements. Here, SimCenter AimSim would be more suitable, where you can create a functional model of the pack with a small number of inputs. You could also import a data sheet where it captures the curves, which you see here, and creates a cell design for you. This might be limited in terms of how it would behave for varying operating temperatures and ranges, but at least I get a fairly good understanding on how my cell would behave at a system level. So to create a more detailed model, what we can then do is collaborate with SimCenter AimSim and Battery Design Studio, where Battery Design Studio is a solution for doing physics-based simulation. So that would be for the electrochemical modeling, as well as if I had, say, test results where I don't know anything about the cell, but I only have the test results, I could still create a cell based on my pulse data to create an RCR model. This RCR model, if you account for varying temperatures and varying C rates, then you would essentially capture the cell behavior for the entire drive cycle. And this file that we create can be imported into AimSim to get a more realistic model. You could also account for the mechanical aspect, such as the cell breathing for a stack-based cell, aging. So there is physics-based aging and there is empirical-based aging. So for the empirical-based aging, we're going to introduce a new feature in the upcoming release where we would be utilizing your test data to create a model which can predict. So we'll use half of your test data to predict all the parameters needed and then fit that data to see how it behaves for the next half of the data to give us more confidence on how it would act. And then I could do thermal abuse. So reactions between the solvent and the electrode, the separator breaking down, and all the concentrations and the heat being released can be modeled to create a thermal abuse modeling. And you can account for manufacturing process, such as how should be my winding layout, and if there is any problem in the modeling of that. The SimCenter PDS essentially has 3D and 1D electrochemical and thermal models with varying material properties for electrodes as well as electrolytes. Electrolytes being very difficult and which truly affects the performance of the cell more than or as equal as the electrode's performance. And this can be extended to do like a design optimization and extended to do a pack level analysis then. So for pack level analysis, I would want to use my cell design, which is in detail, and do a pack level design where I can include all the ancillary material. So say the cooling pad or how the tabs are connected, what would be the tab design, bus bars, and the effects of that. You could use like a lump-based model, but the lump-based model would not capture these contours as such. But what we are able to do is this E-cell is how we discretize our cell. And with that said, I could divide that whole cell into smaller bits, and that's how the resistance is different across that whole cell because the current collector, as the current flows, the resistance varies, and that's how the heat distribution also varies. Here, what you see is if I did a microstructural electrochemistry, I can see how the lithium ion concentration is varying as I discharge my cell. And this gives me the most accurate solution on how the pack would behave. And that I can combine with AIMSIM to create like a functional mock-up unit or FMU, where the star CCM model is talking to the 1D model because I already have the results. The results from the 1D solution is so fast that I get my complete picture on how it would behave at a system level then. Yeah. And then I want to do a design validation of my whole performance attributes, right? And I want to explore for how it would behave at the vehicle integration level. So effects of velocity or effects of water flowing through the coolant path. And I can get varying surface area maps for different load points and using that, I could create that 1D model for different attributes that I'm looking for. I could also extend that to my pack level analysis. So here you see an example where the pack geometry is changing as the coolant path is changing. The idea is to have a more uniform temperature. So initially we started off from 22 kgs of the pack weight. And at the end of the design optimization, I could reduce it to almost 14 kgs. And this combines SimCenter PDS, Star CCM, and AIMSIM. And you can see the baseline versus the improved design. I can see a more uniform temperature. The weight reduced by almost 35%, and the temperature uniformity was 30%. Finally, this is a case study where Quebec wanted to improve on their cooling, mechanical integrity, and how an HPAC would behave as I drive around. So they wanted to have a little more uniform temperature distribution. As you can see, the temperature distribution is not quite uniform, but the air gap is, or the air flowing controls how hot the battery pack would get. And we could control how we should create that vehicle to create a more fluent air path, where reducing the weight was the major driver. They also wanted to design how they could control the expansion and contraction. So what should be the foam size to account for that varying cell pressures. And what we then did is, once I have my new aged model, the temperature rise was around like 10 degrees, whereas for an aged pack, after like say 500 cycles, you could see that the temperature rise was almost 15 degrees higher. And that is something which one needs to account for in terms of if there were questions about reliability. Yeah. With that said, I will pass the ball to Yafis, and we can show a case study in that regard on how we can use further.
Perfect. Thank you very much, Kaushik. Thank you for that clear introduction to battery simulation within the Siemens portfolio. So just give me a moment. I'm just going to share my screen and continue on with the next portion of the presentation. So as Kaushik said, the focus of this presentation is technically going to be on battery pack design in SimCenter Star CCM Plus, but we'll also showcase Battery Design Studio and how it can assist us in generating that battery pack design, but also talk about coupling this battery pack design with system simulation. So to quickly go through what the workflow demo for today is going to look like, we're going to start with creating a cell design in Battery Design Studio. We're going to import that into Star CCM Plus to create the entire battery pack with the thermal management system. And then finally, we're going to integrate that battery pack with an entire overall system design to look at the performance of the battery in not only a singular cell or battery or a given workload, but in an actual drive cycle. So just as we had gone through the first session, we're going to go through the overview, starting with starting the simulation, that is generating the geometry, and that's going to be done in Battery Design Studio. Next, we're going to create the domain of interest and the mesh generation by passing that cell design from Battery Design Studio into Star CCM Plus. Then we're also going to set up all the simulation physics as well as run the simulation. We're going to analyze the data within Star CCM Plus, and then finally drive a design change to push for design exploration. So now we're going to jump into the first step, and that is covering the geometry transfer within Battery Design Studio. So just a quick overview. The first thing, what's important to generating a battery cell within Star CCM Plus is a file known as the TBM file from BDS. It's a text file which contains all the information, including construction, sizing, materials, as well as the physics model. And we're also going to import a PRG file or program file which contains all the details of the battery load cycle. So without any further delay, I'm just going to jump right into the software tool and show you how we're going to design the battery cell. So this is the user interface for Battery Design Studio. Here we're going to create a new workspace, and a new workspace is where all the files are going to be saved in association to that given battery or file. So let me just set up the right directory. Click OK, and let's name this as hands-on simulation. All right. Once you've created a workspace, what you're going to see is the different sections and parts where you can generate the different types of batteries, set up the equivalent circuits, the procedures, and the tests. In terms of the batteries, you can create two different types of batteries, the spiral and stacked cells. And as Kaushik said, you can also create batteries that have only a lump mass, and that's a simple one. For this simulation series, we're going to talk about and just focus on the stacked cell. So once you create a new battery stack, you've got a new battery window that's generated out here. Here, when clicking on the main button, you're going to see the cell diagram. By clicking on the various features, you can look into the construction of the electrode. Here, you can even edit or change the values of, let's say, the tab offset. Similarly, if you go to the negative electrode, you can also make any changes that you want. But beyond just battery formation or the shape of the battery, we're also looking at the material properties in terms of the separators, the electrolytes, the package material. But you're also going to see costing as another feature. So just beyond just looking at the geometry, as Kaushik said, it looks at costing features. You can make equivalent circuits. It has all the material properties within this database. So it's quite an extensive, document in terms of developing any sort of lithium-ion batteries. So when it comes to models, there are two different types of models that are available within PDS. You have empirical and a physics-based model. For this given simulation, we're just going to stick to the empirical model. That's the NTG for a simple discharging simulation. Once you've set up the battery and you've set up all the parameters, all you need to do is right-click and build, and that's going to generate the TBM file. So we're going to use this TBM file essentially to push for the geometry and the material properties into Star CCM+. But just another note, you can essentially create any test you want in terms of thermal test, oven test. You can also do gap analysis and optimization as well. So beyond just the battery geometry, what we're going to do within Battery Design Studio is define the procedure for cycling the battery. Basically, we're going to create an IET or a cycler. This is a simulation model enables you to select current, voltage, and temperature. So once you've created the cycling model, you can choose the different steps you would like. So for this given simulation, what we're going to specify is a constant current discharge of 10 amperes for 1 hour, since the capacity of this battery is 10 ampere hours. So we are going to select a discharge step. In terms of the control conditions, we're going to select current and set the value of current to be 10 amperes. All right. So in terms of the end condition, we said we want to discharge for 1 hour. So we're going to select the time and the value to 3,600 seconds or 1 hour. Now that we've selected the cycle, all we need to do is set up the end button. So this essentially is going to create a PRG file or the program data file, and this file is essentially going to be used to define the discharge or the current discharge. Now you can essentially create as many cycles as you want and make this as required. So I'm just going to save this workspace and jump right back into the presentation. So looking back, what we saw was just we created the TBM file by building the battery geometry and the program file. Now in the next steps, what we're going to do is we're going to use those files from Battery Design Studio to generate the battery within Star CCM+ using the battery simulation module. Essentially, all the geometry, the material properties, as well as the boundary conditions are going to be pushed into Star CCM+ through its inbuilt workflow. So I'm just going to launch Star. Here you can see, the blank user interface. For most of you who've already begun, you might be familiar with this user interface. So it's a client-server user interface where this window is your client and the server is where the simulation is pushed to. Create a new simulation file. Majority of the folks present at the hands-on simulation series would have a power session available to them. So please make sure to activate that to check out the right licenses. Now, once that's complete, click OK. one thing that's different about running a battery simulation within Star CCM compared to a general simulation is that you have a specified workflow specifically for batteries. And to activate that workflow, you have to create a new physics continuum. This right off the bat, when you select the models for the physics continuum, for the battery simulation, we're going to do a three-dimensional simulation, solid, considered implicit unsteady is because we're running an unsteady simulation, and then activate the battery module. Once you've activated the battery module, you can select the energy equation if you'd like to resolve. That's the segregated solid energy for this case, and the equation state as constant density. Once you've selected all the modules, you can see that the icon over here turns from a light gray to a dark gray, meaning that it's solid, and it's blue for being a fluid. Once you've completed selecting the modules, you're going to see a new folder appear, and this is the battery nodes. Here, all the battery cells can be imported, the modules and the program files can be generated. So what we're going to do is we're going to start with importing the battery cell that we had created earlier on using Battery Design Studio. So just jump into session 2. Here, you're going to see a TBM file, and that is the battery cell. We're going to make sure that we select all the parts of the battery, click OK, and now you have the battery cell imported into Star CCM Plus with the full-on geometry of the stacked cell. Now, in this simulation, what we're going to do is we're only going to create one cell, and to do that, we're going to create a new battery module. So once you click a new battery module, you can select the number of batteries you want in parallel in series. As I mentioned, we're only going to do for one cell, but once you've created or you've selected a given configuration, you can right-click the battery module cell and set up the battery module cells spacing. So this is where you can define the spacing in parallel, the spacing in series between the different cells if required. You can flip and rotate them in case you want various other configurations where you want to connect the positive and negative of a different cell in the same section. So in this simulation, as I said, we're just going to start with one single cell, and then we'll expand that into a series of 3 cells. Once you've essentially created your battery module, all you need to do is then generate the battery parts. To do that, right-click your battery module and click Generate Battery Parts, and you're going to see within the parts section the entire battery being generated with all the different parts. So you're going to see the positive tab, root, and stem, the negative root and stem, as well as the stack. Now, note that all the properties associated with these parts are defined by this battery cell over here. You don't have to worry about setting up the properties within the physics module. Everything with regards to battery simulation and all its properties have been imported from the TBM file in this section. So essentially, we've completed the geometry creation of this component. Now we're going to move into the next portion, and that is where we define the region. So just to give a quick overview, we took the TBM and the program files, and then using Star CCM Plus, the battery simulation module, we activated the battery module by creating that physics and generated that battery by taking that cell, creating a battery module, and generating the part. Now that we've completed with this step, we're going to move into the next section, the next section, that is to create the domain of interest. Here, we're going to assign parts to the region. I think most of you are familiar here. Regions is the section where we define the boundary conditions and are associated to a given geometry. We're going to talk about interfaces. We talked about mixing plane interface last time, and in-plane interface. In this place, we're going to talk about in-plane interface between the different solids and the different types of contact interfaces. Finally, we're going to load that program data that we'd created earlier on and create the circuit model to complete the simulation file. So jumping back in to the to the software, we're going to jump right into assigning parts to region. And to do so, we just right click the battery module, and there is a section called assign parts to region. Now, in terms of the parts, this is again, just a recap of what we had covered last session. We're going to create a region for each part, and that's because we want a different boundary conditions for each of the part. Then we want to create a boundary for each part surface. So each part surface will be a separate boundary face. Then one feature curve for all part curves. Again, this is mostly for 2D simulation, and we're just going to leave it as a default. But one thing I would like to focus now, again, is on creating boundary mode interfaces from contacts and create contact mode interface of contacts, and what's the difference between the two. So when you create a boundary mode interface, what it does is that it only creates one pair of boundary and allocates it to the interface. Whereas when you create a contact mode interface, what it does is that it takes as many interfaces that can be allocated to that, as many faces that can be allocated to that contact. To clarify what this means is, let's say you have an electrical board with chips on the board. So you will have two interfaces between the components. That's the components and the board, and the components and the outside or external air domain. If you were to create a boundary mode interface from contacts for each surface between the air and the board, it would have a separate boundary mode or a separate interface. Whereas for a contact mode interface, all the surfaces that are connected between the component and the board are one contact interface, and all the surfaces between the air and the components is one contact interface. This comes a lot into play when we talk about fluid structure interactions. For this given simulation, because we're only dealing with solids, we're going to create a contact mode interface. That means for each of the contacts that are generated, it's going to create one interface. So I'm just going to click apply and close. So let's just look at what's been created. So in the region section, we have the different regions associated with different parts. But as you can see over here, the interfaces, and you have 4 interfaces because it's associated with 4 contacts that are being generated. If this was a boundary mode interface, every boundary that was in contact with the surface would have a separate boundary interface. So now that we've set up the model, the regions are set up, we now need to create the circuit to simulate the response of the battery. So to do so, we're going to import the program file first from our session that we just created. So that's the cycler program that we generated. And as you can see over here is that we have imported the program file, but we have yet to create a circuit element to connect essentially the battery to that program file. So to do so, we want to create first a circuit element for the battery module, and we want to create a circuit element for the program file. And what's going to happen is we're going to see the positive and negative anode and cathode for the battery, and the positive negative cycler. We're going to connect this negative to the positive. So right click, create connection, positive to the negative, and create connection. Essentially what we have just done is connected this cycler program that we had created for discharge and connected to that battery module. So essentially we've already completed setting up the entire simulation. All we need to do now is then mesh and solve for the case. So let's just go back and do a quick review to what we just did. We assigned parts to the regions. We talked a bit about interface and what are the different types of interfaces you can create. We loaded the program data, and then finally created the circuit model to essentially electrically connect the battery to the program file that we had generated earlier on. The next part of the simulation workflow would be meshing. Now, meshing is as easy as a click of a button. So if you right-click the battery module and you set up battery parts meshing, it's going to create an operation essentially, and this operation sets up all the mesh settings that are relevant to this given setup, even setting up volume controls. So this makes it quite simple uh, from a user perspective in setting battery simulation. The only thing what we're going to do is that we're just going to change the base size to 5 millimeters just to run a much coarser mesh for this given workshop. But uh, essentially, setting up the entire meshing process is as simple as just right clicking the battery module and setting up the battery parts meshing. So before we run and set up the simulation, we're just going to go back and touch base with what we just discussed. So in terms of meshing, it's just the click of a button which will set up and generate all the custom controls required for the meshing process. Now, the next step is we're going to talk about is physics setup, the solver parameters, and the stopping criteria. So last uh, last session we had a steady state simulation. So when running a steady state simulation, what you can see over here in terms of the solver parameters or solver criteria, we had steady given out here. But now that we have an unsteady simulation, once you click on that, and this is where you define the time step. So this is over here we can define the time step as 1 second because we're running for 90 seconds. And in terms of uh, other other solver settings, you can find that in the solver tab. Here, if you want to just change the under relaxation factor, you can do that quite easily out there. Then in terms of stopping criteria, this is where we define the maximum number of iterations if we're running a transient simulation. So per time step, let's say we'll increase 15 iterations per time step. And for the maximum physical time, instead of 1 second, we're just going to run the simulation for, let's say, 90 seconds and not the full discharge of 3,600 seconds. Now that we've set up this stopping criteria, what I'd like to do is execute the meshing process. I could have executed earlier. I just did so in the sequence, but you could have just executed the mesh in the previous step. So once the mesh execution is complete, we'll just visualize the mesh, see the mesh that's been generated by this automated workflow. So to visualize the mesh, you can always visualize the mesh by creating these scenes. Scenes can be generated by right click and creating a new scene and creating a mesh scene. This can also be done by this top down menu where you select mesh. Here you're going to create, just a second. Just give me a moment. My computer seems to be hanging. Apologies, folks. There just seems to be a connection issue on my end. I'm just going to reconnect to my PC and we'll be back just shortly. In the meanwhile, if you guys have any questions, please don't hesitate to drop them in the chat. We can get back to you. We can answer some of the questions right now, but if there are any questions unanswered, we can definitely get back to you after the session. these get unlocked the second you turn on the battery. Apologies, I think there was an issue with my audio prior to this. For those who were watching, I think the only thing that I'd like to mention is that we created a scene to visualize the volumetric heat. The scenes can be reached out by looking at the scalar points out here or looking into the field function out there. But once you've created a battery module, you're going to see a new folder essentially with all the new field functions relevant to battery designers. So we're going to select battery volumetric heat to look at the battery volumetric heat on that given phase. The other thing that we would also like to look into is, let's say, the voltage within the given battery cell, so we can create a report. So reports are essentially scalar quantities that we can extract from the module. So as you can see, we can look at circuit voltage, current, and the current derivative. This is because once we've activated the battery simulation module, it unlocks the physics solver to calculate such features. So we're going to create a user function of volume average, looking at the volume average voltage within the battery. So just look at battery volts. All right. And in terms of the parts, we're only just going to select the stack region of where we want to look into this. I'm just going to rename this as volt. Now, once you've created a report, you can essentially run the report, and it would give you that exact value at if anything was calculated. If I do run the report, it'll give me a 0 value and on value because we haven't computed anything yet. But essentially, this gives you a singular value that you can extract data from. But what if you want to monitor or collect that data throughout the simulation? You can create a monitor from that report, but at the same time, you can create a monitor and plot from the reports, which will create the scene essentially. So we've already created the voltage plot as well as the scalar plot for the volumetric load. What I'm going to do is there's also one thing I'd like to mention is whenever you look at the voltage monitor, because it's a transient setup, it's automated the trigger as time step, and it's going to extract that voltage monitor every time step. But just to verify, you can do that any delta time, any iteration. But in this case, we're going to use a time step as a trigger to when we want to extract that voltage monitor, and hence voltage will be plotted against physical time. So we're just going to run the simulation, and you can see the solution being updated in real time. One thing you'll notice from this plot is that the temperatures that are much higher next to the tabs as expected. So essentially, this is a quick and easy method of running a full battery simulation within less than 20 minutes. We're able to create a battery file, import it into StarCCM+, use that battery simulation file to then generate a whole circuit model and test essentially the performance of the battery in a discharge cycle. So moving back to the presentation, what I want to do for the next portion of the simulation is essentially take that one single battery unit and run a string analysis, that is 3 batteries in series. And what we're going to do is we're going to leverage the same simulation file that we just used. So I'm just going to stop the simulation file. We're going to clear the solution. So that's solution clear, and we're going to clear all the fields. Now what we're going to do is ensure that we basically set up a string simulation. So what we're going to change is in the battery module, instead of 1:1, we're going to run 3 in series, and it's going to create additional tab connections between the different components. So to essentially, the other thing we want to do is we want to set up the battery module cells, how these cells are going to be set in offset. So apparently there's an offset spacing of 1 millimeter between the batteries. We can set that. So you can see the offset's been set. but also what we want to do is we want to flip the middle cell to make sure the positive of the middle cell is next to the negative of the first cell. So we're going to apply and close. Next thing that we would like to do is have tab connections to essentially set up tab connections between the cells. So what I'm going to do is I'm going to import a tab connection that was earlier generated. So that was created before. This is a simple tab connection. All right. So we're going to import this tab connection, and we're going to use this tab connection to connect the different uh, cells. Once you've imported, you want to set up the tab connection. So right click the tab connections and set up tab connection. Here you the copy of the single tab connector, and here we select the different parts. So for the first post part, we're going to set up the negative tab connector. For the strap, we have the strap of the tab connector and the positive of the tab connector. So all we're going to do is hit apply and close, and we're going to generate the parts. So we're just going to right click, generate the battery parts, and what you're going to see is the additional batteries have been generated. So you're going to see cell number 1, 2, and 3, as well as the tab connections, which we're going to generate in a moment as well. So we just created the battery parts. So right click and generate connector parts, and you're going to see the different. So if I just highlight these, I'm going to see the 3 different batteries and the tab connectors connecting the different batteries. The next part, what we're going to do, so just an FYI, once we've generated the parts, what happens is that the region just needs to be reselected because we recreated the parts. So for the first battery, that module we selected, we're just going to select the different regions associated with the different parts. Just bear with me for a moment. So this is selecting the regions for the root and stem for the positive, and now root and stem for the negative. All right. So once we've set up for the first cell that we generated, what we need to do now is create the regions for the other components. So first thing, I'm just going to delete the previous mesh generation we did. But what I'd also like to do in terms of operations, I want to create an imprint operation. And what this imprint operation, as I mentioned earlier on, is to make sure that the mesh between all the different components is conformal. So I'm just going to select all the different parts, which are then going to ensure that there's a conformal mesh between the different components. So just because I'm going to set the tolerance to a much lower value, just because the tabbing connectors are at very close proximity. Once we've executed and created those imprint operations, it's just going to make sure that those contacts exist between different components. Now what we need to do is assign the parts to regions. So we're going to right click out here, assign parts to region. We're just going to deselect the first module because that's already been generated from the previous simulation we ran. We're going to create a region for each part, create a region for each part surface, and create contact mode interface from contacts as we had done earlier on. Click apply and close. We also need to set up the meshing, so you see all the regions created for all the different components automatically, with reducing user error significantly. We're just going to right click and set up the battery parts meshing. Again, this has been automated, selecting all the different parts for the batteries. Here we're just going to change again the default size to 5 millimeter. And in terms of mesh scene, we can essentially just leave the same monitor plots to look at the voltage of the first mesh scene and the scalar scene of the stack components. I'm just going to execute the meshing module just to ensure that all the components are meshed correctly. And now, in terms of the circuit model no longer needs to be changed because the positive and negative side of the battery are as is, and the cycler are connected to those positive and negative since we created an entire battery module out of it. So it's pretty intuitive in terms of creating battery simulation. Within a few clicks, we were able to convert that from a single cell into a 3-part battery module. Another feature that you can do is you can import an external casing or have an external casing specification if you'd like. So these features in this entire pipeline workflow within Star CCM Plus enables you to run battery simulations with a few clicks of a button. So what I've showcased right now was just a single cell, and what we're going to do is essentially complete the meshing process. I'll run the simulation just to show the post processing. But what we're going to do in the next part of the presentation is to look into the design change. Now, what if we were talking about a more complex battery pack? I've already pre-built that file, and we're going to look through that in a moment. Just bear with me for a second, and once this is complete, we're just going to run the simulation just to ensure that everything has been set up correctly. Again, you're going to see the temperature is pretty high along the tabs, and it's along the same temperature that you expect for the single battery in series, and that's expected as a single cell as expected with the 3 batteries. And here you can see the voltage monitor plot with the discharge pretty steady in this case. So that sort of marks the end of my presentation when it comes to setting up the module in for a single cell series. But what we're going to focus now on is to go beyond just a single cell, but also look at a battery pack in a with thermal management system that's a cooling channels. We'll look into making a design change and looking at how that updated geometry affects the performance. But beyond just looking at how it's updated the performance, we're also going to look into the design manager and how design manager can be used to find you the best design possible based on your objectives and constraints. So I'm just going to stop the simulation and jump into the model that I'd like to present today. So this is a battery consisting of two cells in series and parallel. So very much similar to what we had done before. Imported a TBM file which has an RCR table 3D unit cell model. You can see that over here in the battery module we've selected 14 cells in series and 2 in parallel. And in this case we've set up a module current. Instead of a program file, we've created a module current over physical time just to look at the performance of this cell. Now, what I'd also like to show is, the CAD for the water cooled. So you're going to see these are water cooled channels that are provided. But again, like we had done in the previous session, we do have CAD parameters that we can update and connect, but as this is connected to another part that's available. So you can update change the parameters and update the geometry to drive this geometry from your CAD into Star CCM Plus. So this is using the bidirectional CAD associativity with NX. Now, I'd like to show you some of the features in terms of post processing. This solution has already been run, but if you scroll down all the way to tools, you're going to see a new folder called layouts. So layouts are essentially windows that you'd like to save to analyze data. So you can essentially create new layouts if you go to layout views, you can create a new view by looking, by separating windows of different features. So let's say I want to create top to bottom. Just to give you a quick example, out here I'm creating this layout view. I'm going to create, and in this layout view, I want to put some scenes essentially. So I'm just going to go to the scene. Let's say I want to look at cell temperature out here, drag and drop. But beyond that, I'd also like to look into a plot, maybe look at module, and this is where you can visualize different types of windows at the same time. But then you can also then save these layout states to be reused later. So there have been some layouts that have already been generated. So if I expand on layouts and I want to look at analyze layout, I'm going to restore the layout, and it creates this sort of window where I can visualize my data and compare different data points. So out here you can see that this is an animation of the fluid flow. Out here this can be paused and stopped to this animated window over here. So in the next part, what we're going to do is we're going to drive a design change. Let's make changes in the geometry and refresh and restart the remesh the geometry and then run the simulation. For this section, the second part, I've already set up a recording, and just because of the time constraint that we have, so I'm just going to show you exactly what was done in that recording. What we did is that we took the same geometry that we looked into live. We looked into the battery pack, made changes to the cold plate. Here, one thing that's key to mention is that you can choose the any type of parameter within your geometry to drive that change. And these parameters can be not only limited to geometry, but also you can use any operations. There are a bunch of operations that are used to drive this change, but once you've made the geometry changes you're looking for, as you can see, the channel is a bit offset. You can update the mesh. Once you've updated the mesh, all you need to do is run the simulation, and it's just going to start the simulation from a given profile. Or if you want, you can clear the solution and run it from scratch. But this is quite simple in a few steps, where you can just change the parameters and be able to drive design change. And this is exactly what the mesh to CAD pipeline in Star CCM is all about. And all you need to do is, once the meshing is complete, all you need to do is run the simulation, and the new solution will update. So going back into the presentation, what I want to cover in the next portion is design exploration and how to drive intelligent design exploration. In this given simulation, what we want to do in terms of objectives are two things: minimize the pack weight and minimize the coolant channel pressure drops. We also want to make sure the maximum temperature is less than 60 degrees, as well as the maximum temperature difference is less than 3 degrees Celsius. So let's just jump into the software and try to create the design manager project with these given objectives and constraints. So this is our given simulation. Okay, so this is our given simulation, and what we're going to do now is create a new design manager project, and this is what we're going to use to set up our optimization study. All right. So in the design manager project, here you can create different types of design studies. I'd covered some of those last week, but essentially we're going to create an optimization design study for this given case. So here you can select the type. There's sweep, optimization, stochastic. You can look at CAD robustness. In this given problem, maybe certain CAD parameters when changed would break the geometry, so you can test that out here. So we're going to look into optimization. Now, in terms of input parameters, we said that we have 4 input parameters. We want the pack weight. So let's just expand the parameters and look at what we see. All we see is all the different components of the parts. So let's say in terms of the geometry, what would we like to import? We could import, let's say, the channel thickness, the width. Let's say we want to look into the cell width as well. We could also import all the different types of geometry parameters, and we could modify each one of them to drive the design study. So for this case, I'm not going to actually run the study, so select as many input parameters as I want. But in terms of the resources, let's look at this. So all the reports that we generated are available to us. So once we've given a design change to those parameters that we just showed, you want to look at some response. So our response would be minimizing pack weight. So that's going to be out there. We want to minimize the coolant pressure drop, so the pressure drop. But we also want to make sure that there are 2 constraints. So the maximum temperature is less than 60 degrees, and the maximum temperature difference is less than 3 degrees. So we have created reports associated with these parameters. click OK. And from these resources, as we said, so the pressure drop, this is a objective. We want to minimize this. We can expand. The objective is to minimize. You can put a weighting factor if you would like in terms of the maximum temperature. This is a constraint. We want to make sure the constraint properties are a maximum value of 60 degrees. And in terms of model temperature difference, we want to, so this is a constraint. We want the maximum temperature difference to be less than 3 degrees. And as simple as that, we've already set up the entire, last thing is the objective over here is to minimize the pack weight. So, and now we've already set up our design study. Everything, in terms of input parameters, one thing I did need to mention, you can select what values you would like to modify for each one of them, set them as continuous, discrete, or constant values if required. And then finally, in terms of scenes, for each data point or each simulation, what would you like to save? Let's say we want to look at the mesh, the cell temperature, and the channel velocity. We can also look into plots. For each given simulation, we'd like to look at the pressure drop, the temperature difference just to make sure it's converged, as well as the module voltage. And in terms of settings, this is where you set up the run settings, what type of compute resources you want to use, depending on whether you want it direct or do you want it to a cluster, can be easily pushed there. And how many simultaneous jobs you want to run with how many compute processes per job. So all we need to do at this point is right click and run the design study. So just to show you the results. So like I mentioned, the objective was to minimize pack, minimize the coolant temperature. The constraint was maximum temperature should be less than 60 degrees, and the maximum temperature difference is less than 3 degrees. So looking at the design study, this is what was achieved. As you can see over here, for each given point, for each simulation, the files are available, the scenes. Anything that's blue is feasible, anything that's red is infeasible or has crossed the constraints. And from this given graph, you can basically select a design of minimum pressure drop and decreased weight. And this was all done embedded within StarCCM Plus, and no other tool was essentially used for this given simulation. Just to give you some background, it took 3 days to run this given simulation, 10 simulations on 10 into 12 CPU cores, basically 10 runs simultaneously on 10 CPUs, which NX was run on Windows to drive the CAD change, and Linux system of 2.4 gigahertz was used for running the simulation. So looking back into the workflow demo for this battery, we analyze the battery as, as an individual component at the given current cycle and, with a given load. But however, these conditions are essentially based on some given profile. And in real life, simulations or situations, the profiles are constantly changing. So batteries are generally part of a complex system. They're multi-domain. They contain control systems, hydraulics, other electrical systems, to name a few. And essentially, the challenge we face is how do we virtually verify a complete system and not just components? And this can go beyond just battery design. Right now, we're looking at a given, battery within, let's say, a vehicle, electric vehicle, but we could look into, let's say, a cooling system or a pressure drop device in a full, car system that could be in the controller as well. So the idea over here is that this sort of simulation where we want to look into the performance of a given component in a real life behavior that is looking at the different interdependent domains, we can only accomplish this essentially by multi-physics system simulation. And I think Kaushik gave a great overview of what that was. And so within our solutions portfolio, he talked about Amazon, which is an integrated scalable system simulation platform that allows you to do such multi-physics simulations that combine electrical, thermal, hydraulics, mechanical, and controls to essentially virtually assess and optimize an entire Megatronic system's performance. Now, because the Amazon tool is part of the SimCenter portfolio, it is well connected with Star CCM Plus, and it can connect to more detailed solutions beyond just 3D, but also FEA analysis. So to give you an example, this is in, let me show you how this works in practice. Here we have a a battery system in an electrical vehicle. The radiator basically is responsible for cooling the fluid that comes from the battery system is fed back into the battery system, and you have a given velocity profile of the car. So based on that velocity profile, the radiator is going to have some sort of cooling profile, which then defines the cooling system in the battery. Now, in Amazon, we're representing the entire cooling system. It provides the temperature and mass flow boundary conditions at the inlet of the battery pack. And in Star CCM Plus, it calculates the heat flux from the pack into the coolant. So it provides the coolant outlet pressure and temperature to Amazon, which then goes into a three-way thermostat and back into the radiator. So what I'm going to do is I'm just going to launch the Amazon tool just to show you the features out here within the software live. So as you can see over here, this is the same diagram that I had shown it earlier. What we have over here is the TCP control that connects the Star CCM to Amazon. It's pretty much connected through a port server. In this given example, you have different port numbers that are defined. The port number 1 is where you export the temperature. Port number 2 is where you export the pressure. Port number 3 and 4 is where you have the mass flow rate, the inlet mass flow rate, and the temperature that comes from the system. So you have a velocity profile of the given car that's fed into this radiator. Based on that, the cooling of the temperature and the temperature and the mass flow rate from the radiator is fed into the battery cooling system. So let me just open the Star CCM model. So this is the Star CCM model. Again, we use BSM to create the entire battery cell as well as the battery module. Just a few other things about this given geometry. You have the entire fluid domain created through operations within Star CCM Plus. So you can create new Boolean operations. And so that's exactly what that was used through the different parts out here. So once you've created this domain, let's just look at some of the other things. Example, the regions. This is where we set up the boundary conditions. If you look at the volume out here and we look at the inlet condition, let's just expand the boundaries and look at the inlet condition. It's been defined by a field function called applied mdot. So we'll just look at that shortly, how that's defined. And in the outlet extension, we have the boundaries, and so the outlet that's defined by another field function out here. So the outlet boundary conditions. The outlet boundary conditions here. You have we have to export the outlet boundary condition to Amazon. So I'm just going to show you how that is. So to activate the connection between Amazon and Star CCM Plus, all that's needed to do is in the continuum, right-click, select the models, and you can see there's an option over here called co-simulation. Once you select that, you select SimCenter Amazon. You can create co-simulation with other tools. We have an explicit coupling, and that's all that's needed to activate the connection between Amazon and Star CCM Plus. So once you've created this coupling, if you look into here, you're going to see a new folder called external links. This is for connecting Amazon. So you can see here is the link between Amazon and Star CCM Plus. How that's defined is through the Amazon model, and I'll explain to you shortly how that is connected. So in this field, we created certain exported fields, and these were reports that we have already generated. And in terms of the imported fields, we're getting two imported fields. And like I mentioned, port 3 is to do mass flow rate, and this is port number 4 is to do with the temperature. and only association between, and you can see the association and associated IDs that connect basically those given ports to those boundary conditions. And in terms of the values, you have the connection settings where you select a port number out here. And if you look at the TCP IP out here, there's a port number that needs to match. So what's going to happen is that these 4 data points are going to be essentially saved on the server port, and this is how the exchange between Star CCM Plus and AMSN takes place. So pretty much, hopefully you've understood and covered exactly how this model was set up. You have this external link where the different imported fields and exported fields are set up, and essentially all we need to do is set up the field functions or the imports as the inlet conditions and reports as the outlet conditions. And now to essentially run the two simulations, all you need to do is go to the external link, right click and hit connect. So it's going to look up. I forgot to start. So you need to start the port out here. So you can see it started, but it hasn't essentially begun because it's waiting for the information from Star CCM Plus. Right click and connect. Initialize. And the connection select successful. Sorry, I declared the solution because there was data point. Now that the solution is connected, we're going to run the simulation. Here, as the solution is iterating, you can see that the solution in AMSN is going forward in time space as well. And this is, so every data time point information is set here, and it comes from AMSN. So it's as simple as that. Isn't too complicated setup. And so essentially, if you want to visualize any of the 3D data, it can be visualized in Star CCM. And if you want to visualize any of the 1D data, you can see that in AMSN. So I'm just going to show you some of the results in live. So these are the results that I posted from earlier. So you're looking at the solution in real time in 3D. And if you want to then look at, for example, the results in 1D, here are some of the graphs. So you're looking at the coolant mass flow rate to the radiator, as well as the temperature of the inlet pack. So essentially, this marks the end of today's session.